Thank you, Bice, and thank you to the organizer to inviting me to this very interesting session. So I think that also in our country the topic on nanoparticle exposure is very hot, and I think that I will try to summarize some concept and okay, thank you. Some concept regarding the evaluation of hazard and how we can move towards the risk assessment procedure to control in occupational settings some possible exposure and relating risks. Although the current production of engineered nanomaterials is small, the global production is expected to grow in the next few years, being fueled by a worldwide growth in research and development, which is seen as the key to industrial innovation in many sectors. In terms of human resources, nanotechnology development is likely to require an additional 2 to 10 million workers across the world by 2014. Many of these jobs are likely to be created in Europe, mainly in startup companies and in small and medium enterprises, which usually apply poor control of chemical risk. In our country, the second census of nanotechnology operated by AIRI, Associazione Italiana per la Ricerca Industriale, gave a similar picture, so a very involvement in micro and small enterprises. As a whole, this technological development could increase also the potential of exposure and raise concern about additional potential risk to the health and the environment. But we have two key questions to put. Do these new nanomaterials present new safety and health hazard and risk? How can the benefits of nanotechnology be realized while proactively minimizing the potential risk? The problem is that there are established protocols and terminology surrounding how to assess risks and what standard of proof must be met. Accepted and standardized tests and models are now in place to allow for an evaluation of any processes of materials against existing benchmarks and to categorize their associated risk level. The central concern is whether or not these established benchmarks can be used to adequately assess nanomaterials and nanoproducts. We have, starting from the hazard, hazard is a property inherent in a substance or situation with the potential to cause effects when an organism, a system, or a population is exposed to this agent, whereas risk is the probability that the effects will occur on an organism, a system, or a population in specific circumstances. It is, we cannot forget that there are also safety risks posed by the nanoparticles, nanomaterial in general. It is well known that an explosive or flammable dust cloud can be formed from organic or metallic materials or certain other inorganic compounds. One of the main factors influencing the ignition energy and violence of an explosion is just the size or area. Many nanoparticles meet this criteria because of their chemical composition and very small size. They could then exhibit explosive potential and flammability. Given their large surface, they could also have a catalytic potential that can translate into an uncontrolled reaction. Other risks are also likely to be linked to their instability or their chemical reactivity. Anyway, it is also known that condition required to produce an explosion depends on both particle type, chemical and surface composition, size, combustibility, but also from environmental conditions. Several organic substances like metals, including aluminium, zirconium, lithium, and some inorganic substances are particularly at high risk. But the other side of the complementary side, the hazard, is that of health issues. Because several studies have been performed, especially on animal species and in cellular model, to determine whether nanoparticles can have toxic health effects. Generally speaking, nanoparticles soluble in biological fluids dissolves, and their toxic effects are related to their different chemical components, independent of the particle's initial size. These effects are well known, depending on chemical composition, and are not specific to nanometric dimensions. But on the other side, the situation is completely, or may be completely different for nanoparticles that are insoluble or very weakly insoluble in the organism. The data currently available on toxicity of insoluble nanoparticles are extremely limited and normally do not allow a quantitative risk assessment or an extrapolation to humans, except possibly for few classes, like, for instance, titanium dioxide. But the health risk depends not only by the intrinsic hazards. We should be evaluated according to the physicochemical and biologically relevant nanoparticle and nanomaterial properties, but also by the likelihood of exposure, defined as the contact over time and space between a person and one or more biological, chemical, or physical agents. Primary considerations in exposure assessment are thus the likelihood, the magnitude, and the routes of exposure, which, in occupational setting, include inhalation, absorption to the skin, and ingestion. The unintentional exposure to nanoparticles is not new phenomenon in occupational settings, since it is well known that certain workplaces conditions generate aerosols characterized by high concentration and a very high number of nanoparticles falling in the inhalable range. But the new nanoparticles that are produced intentionally, and some producers have developed nanoparticles with low tendency to agglomerate. In a sound process of risk analysis, detailed knowledge of the type of nanoparticles handled and their toxicity, the potential emission scenarios, as well as at exposure levels and the safety risk at the different workstations and for all tasks should be considered. Risk analysis includes different complementary steps and is part of a comprehensive approach intended to control the risk factors. In all nanoparticles producing processes, there is the potential for exposure to occur at both the synthesis and recovery phase of the process. Process generating nanomaterials in the gas phase or using or producing nanomaterials as powders, slurries, suspension, solutions pose the greatest risk for releasing nanoparticles. Maintenance or production systems is likely to result in exposure to nanoparticles if it involves disturbing depositing nanomaterials. Work with nanoparticles can lead to the formation of inhalable airborne aerosol. Work in a wet medium substantially reduces the potential of generating aerosol in the air without totally eliminating heat, and it should be used every time it is possible. But also the cutaneous contact is possible in various situations, especially in the presence of liquid suspensions. Among the many workplace factors that and operations, they may increase the potential for exposure to nanoaerosol. The National Institute of Occupational Safety and Health has listed the following. But this slide, for instance, provides some examples of job tasks exposing workers to nanomaterials. The health effects of nanoparticle exposure are not closely related to the mass of the particles. And there is no currently international consensus on the best approaches to use for characterization and assessment of occupational exposure. It becomes more important to characterize nanoparticle emissions and, as a minimum, to estimate the concentration in number of particles, size distribution, specific surface area, and chemical composition. Currently, it would be prudent to establish the aerosol mass exposure also by granulometric fraction, so as to have maximum information to allow assessment of exposure. In spite of uncertainties about metrology and the lack of internationally recognized occupational standards, some field studies have provided preliminary data useful for a quantitative assessment. They are made by several institutions worldwide, for instance, by the National Institute of Occupational Safety and Health in different contexts, but also by the German Federal Institute of Occupational Safety and Health, for instance, that made a lot of study on plants. It is interesting to see that the airborne concentration of titanium dioxide detected at the beam filling operation revealed that during the normal operation, the number concentration were up to 30,000 per cubic centimeter, and that particles were most aggregate or agglomerates with primary particles in the order of 25 to 100 nanometer. But as compared to the threshold limit value for dust, these such results seem very low and safe. But however, during leakage at the same plant, concentration up to 150,000 per square centimeter were recorded. And due to their plausible higher toxicity, recommended exposure limit for ultrafine nanomaterials should be lower than limits for fine nanomaterials. In the case of titanium dioxide, that is to date the only one example, the National Institute of Occupational Safety and Health recommended an exposure limit of 1.5 milligram per cubic meter for fine particles and one of 0.1 milligram per cubic meter for ultrafine particles. Similar studies have been made also monitoring exposure to carbon nanotubes during carbon nanotube manufacturing. And this study, the pioneer study made from Maynard, gave airborne concentration of some tenths of microgram per cubic meter, but the material on individual gloves, for instance, range from 200 to several thousand micrograms, so indicated that cutaneous exposure skin exposure is possible. Interestingly, carbon nanotubes manufacturers and suppliers classify this new form of carbon as synthetic graphite. That is a compound of relatively low toxicity. So the material safety data sheet reference the permissible exposure level for synthetic graphite of 5 milligram per cubic meter for the respirable fraction. So that carbon nanotubes are simply defined as irritants. It can be estimated that a worker breathing 0.0 milligram per cubic meter would take about 3 years to reach the alveolar burden of 5 milligrams of carbon nanotubes, also assuming no pulmonary elimination occurred. This exposure regimen, at least in animals, is expected to produce some lung lesions. Thus, the permissible exposure limit of 5 milligrams per cubic meter set for respirable synthetic graphite dust cannot be recommended for carbon nanotubes. Until data from inhalation study are available, The NIOSH recommends that the occupational exposure limit for respirable carbon nanotube dust be set at a value no greater than 0.1 milligram per cubic meter. Despite the large uncertainty, we can also try to have by different instrument qualitative assessment of exposure. For instance, by the interview. Also, Michael in recent year make a very interesting study about that. After gathering and interpreting all the available information of nanoparticle toxicity and the occupational exposure condition prevailing in the work environment, it should be possible to estimate the risk of adverse effects. In the vast majority of situations, the data are insufficient to be able to predict the precise effects related to their exposure, especially in a context where the majority of studies have shown certain toxic effects in animals with acute exposure. In a context of major, there is almost no knowledge on the chronic risk, chronic effect associated with nanoparticles. In a context of major uncertainties regarding the specific toxicity of nanomaterials and the lack of occupational exposure data, the quantitative risk assessment is actually impossible in most cases. In such a situation, a preventive or precautionary approach must be put in place. However, some alternative approach and quantitative risk assessment, or qualitative better risk assessment, where the level of control is adapted to estimate the level of risk, is also possible. To be able to implement safe but realistic means of control in relation to the risk, a new approach was developed in UK in the 10 years ago. Its use is becoming increasingly widespread. It is the control banding. The slide shows the matrix of the control band in relation to the severity and probability. This simple but effective tool makes it possible to take into account all the available information, toxicity, exposure level, and to develop logical hypotheses on the missing information. The model is based on the use of a limited number of factors for evaluating the risk level in order to reduce the complexity and increase the applicability for non-experts. The control strategy is limited to 3 levels or bands of engineered controls, referring to control banding, based on solid foundation in occupational hygiene, okay, to which is added a 4th control band that requires the intervention of a specialist for most hazardous situations. Each control band can then be estimated from an overall score to be determined for each task, and that takes into account severity aspects, so the score related to the toxicity, and probability aspect, the score related to the probability of exposure or the potential exposure level. This is just an example of a table for calculating the probability score, and I go through. Okay. The control of risk factor or risk management is a proactive behavior in a context of multiple uncertainties regarding both health risk and exposure level by adopting a hierarchy of control measures. The means of controlling exposure must consider all the work-related aspects: installation, processes, equipment, activities, tasks, workstation, and workers' movements. The principal elements of each of the 3 main risk control categories are illustrated in this slide. Note that engineered techniques are normally more effective than administrative measures and personal protective equipment because they are independent on the workers' behavior and prevent the possibility of contact between the pollutant and the workers. Such a hierarchy of measures is as applied to inhalation and dermal risk comprises elimination, substitution, process enclosure, engineer control, mainly industrial ventilation, but also administrative measures. I mean the reduction of number of exposed workers or the time spent by workers on the process to implement the implementation of good work practices. The personal protective equipment must only be used as the last resort when the engineer techniques and administrative measures are unsatisfactory to protect the workers. Particular attention must be paid to the specific needs for maintenance personnel who often have the access to locations where the exposure level could be significant. The field studies have been shown that sporadic or accidental airborne nanoparticles emanation is possible in certain processes or operations because they are not always performed in a fail-safe, airtight closed circuits. Current knowledge indicates that a well-designed exhaust ventilation system with a high-efficiency particulate arrestor (HEPA) filter should effectively remove nanoparticles. When particles are very fine, the diffusion forces become significant and their behavior is similar to the behavior of a gas or vapor. For coarser particles, inertial forces tend to dominate. But the general ventilation must not be considered as an effective means of elimination of toxic nanoparticles from a work environment, unless the risk could be quantified, and it is proven that this technique, coupled with a fresh air intake, is enough to maintaining ambient concentrations well below the quantities representing a significant risk. A major drawback is that to manage the risk is that currently no specific exposure limit exists for airborne exposure to engineered nanoparticles, although occupational exposure limit exists for larger particles of similar chemical composition. Although safe handling procedures are paramount, it is believed that additional efforts to monitor employee health should be warranted in the near future. There are arguments pro and contra nanospecific medical surveillance, its feasibility and appropriateness. At present, it is unclear what kind of health surveillance can be suggested for nanotechnology workers. It appears that nanoparticles can exacerbate certain pre-existing medical conditions, such as cardiovascular diseases, and may increase susceptibility to some diseases which may require modification of testing strategies. For instance, the models of health surveillance proposed by the NIOSH is intended as a systematic collection, analysis, and dissemination of exposure and health data on groups of workers. It involves several steps, such as ADA surveillance, medical screening, and medical surveillance. But the decision on medical surveillance requires at least a qualitative risk assessment, and thus should be implemented when a residual risk exists and the target population is clearly identified. There is now a satisfactory level of awareness among stakeholders that workplace where nanomaterials are intentionally produced, processed, used, disposed, recycled, may pose specific challenges. We don't need a revolution of the existing risk assessment framework or regulatory approach, but just an evolution. Responsible management of nanotechnology development inevitably depends on the preparation, implementation, monitoring, and continuous improvement of an industrial accident occupational disease prevention program in the work environment, based on a precautionary approach with the goal of minimizing risk they cannot be determined precisely. To have an impact, the prevention program must be part of the facility fundamental values, culture and development plan, meaning that occupational health and safety represent an action priority, the management and all employees are fully committed to it, the necessary efforts are made to achieve the prevention objectives. In the 2006, Nature published an article written by a leading scientist that outlined a list of 5 grand challenges to ensure the safety of nanotechnology. This addresses research needs in the areas of exposure monitoring, instrument development, toxicity testing, predicting nanoscale material impact, developing life cycle approaches to using nanotechnology safely. And finally, as nanomaterials grow in application, it is increasingly important to continually ask questions and assess the impact on human health and environment, so that risk can be managed and avoided. Nanomaterial safety assessment is a continuous process with no clear beginning or end. Thank you for your attention.
Thank you. I think the best thing is to have the 3 talks.